Cool. Like synchronous is basically induction, but without the fact that the rotor part is not like bars. It actually have a magnetic field from a source there. So if just think of induction, take out the squirrel cage and you put in an electromagnet there and you put in a source to provide the energy for that rotor magnetic field. That's literally different. And everything is basically the same concept. But instead of chasing, you're actually catching the person and running at the same speed now. So it's the same concept, but one is chasing and one is I'm gonna catch you and now we're gonna run together in harmony. So cool, right? So this is just theory, it could be a generator or a motor. So most of the time with the synchronous machines, you use a synchronous generator more than a motor. You could use it as a motor, but in most applications you'll use it as a generator, right? So for a generator, you need a prime mover. So you connect the prime mover to the shaft of the synchronous generator. The shaft will turn, and with the shaft now, you basically have a source that giving it a magnetic field. So now with that turning, you're turning a magnetic field, and those magnetic field lines cutting the coils of the stator, and then now when the magnetic field cut the stator windings, they induce a EMF, you get a current, and how the three-phase stator is wired, it'll actually give you a three-phase power out, A, B, and C phase. So it's basically just a synchronous generator with a prime mover. And that's basically how they generate power. So power gen and all those big power producing companies, they basically just use turbines. So they just burn the oil, they burn the gas, and it will just they compress the gas, will turn the turbine spinning at the prime mover, and everything is just a synchronous generator, right? So all this is theory. So mechanical terms, but you know the rotor is the rotating part, stator is the stationary part. The two things you have to remember that will change depending if you have a generator or a motor. The armature is the power producing component of the generator or the motor. So the windings that produce motion or induces a voltage. You have to remember this, right? And the field is the magnetic field component of a generator or motor. It can either be an electromagnet or a permanent magnet, right? Either way. The electromagnet, you have an external source, and while the permanent magnet is just a north and a south pole that always north and south, right? All these are just definition. Just know the definition because he could just ask to define these terms in the exam. And also he could use wordplay, and the wordplay does confuse people. So yeah, so you went to the address now. You have the stator, that's basically just a rotating magnetic field. Well, there's in a motor application, right? So you have the rotating magnetic field in the stator. Same thing, it's spatially divided 120 degrees apart from each other. Just like the induction, same concept. The supply is a three-phase supply. Three-phase 120 degrees apart from each other. That will never change. Okay, so the rotor, well, I mean, most of the time you connect the rotor to a DC supply because you need the rotor to have its own magnetic field. That is important, right? So you have two types. You have salient pole and well non-salient pole. I don't want to put all that in the slide because of length, but make sure you know the differences and the advantages, disadvantages between salient pole and non-salient pole rotors. Yeah. So salient pole is basically ones that look like a big T, like we are accustomed to it, and the non-salient pole does look really nice. But just know the differences between them. Advantages, disadvantages, just know them. You never know if you don't ask it in a theory question. Okay, cool. So the principal operation, I will you can read through this by yourself, but it's the same concept. Three phase into there's a motor. So if you have a three phase into the stator, it will produce a rotating magnetic field, just like the induction motor. But now in the rotor now, he has her or him his own magnetic field there from the external source. So think about it like you have a rotating magnetic field, and now the rotor have its own magnetic field. No induction going on in between the rotor and the stator. So what actually happens, just to keep it simple, so this is your stator, and your rotor now you actually can produce a little magnetic field now. And what basically gonna happen is this gonna lock on to each other. And when it lock on, it will basically rotate at the same speed. Yeah. So when it lock on, it might have a little angle because if you lock onto something, it mightn't be exactly parallel to each other like how I do it here. It might be off by a little bit, and it actually have a name for that. So it might be like somewhere here. So you have a little difference. And the same thing for the notes, it might have a little angle between what you're chasing. Yeah. It wouldn't be always parallel or like right in line with it. And it have a definition or a name for that angle. But I digress. But basically, what's going on is that the rotor magnetic field is locking on and basically following the rotating magnetic field of the stator. Yeah, well, basically, Lorentz law basically telling you that a force will be induced and you get rotation. Yeah, that's really all. When it lock on, you basically rotating and it's shuffle too. Cool. So that's the generator is basically the same concept that's reversed. So now we have a prime mover and it basically rotating something with a magnetic field and it will just produce a three phase, which is just the opposite. So if I read it through, it's basically just Faraday's law. When you have a rotating magnetic field cutting a coil, it will induce an EMF. But if you wire three coils that are spatially 120 degrees apart from each other, and you rotate that same magnetic field, it will then now in each coil, it will produce a three-phase power that each coil is 120 degrees apart from each other. It's real cool. But you need a prime mover to do that. So it's a generator. Right, all them things are just theory. And same thing here, theory. They're just showing you the generator application of it. Yeah, so you need a excitation voltage into the rotor, and now we just need something to turn the rotor, which is the prime mover. Yeah, same Faraday's law that I use, and then it just produce three-phase power, just like we did before. Right, same concept, the synchronous speed between induction and synchronous, the same concept, the same equations, right? It really changed. 120 F1 P or 60 F1 pole pair, same equation. Exact same equation, right? Now down here, just kind of like showing you the difference if you have a generator and a motor, but really and truly, once you have NS and F, you could go anyway. It's the same equation from before. Yeah. Okay, equivalent circuit. So this is the equivalent circuit of a synchronous machine. So the equivalent circuit is basically the same thing for both of them, but what changes is what is at these 2 points here. Yeah, so this is the equivalent circuit. So this part here is your rotor. So this turning. So if your rotor turning and this here is your stator, this would be a generator. Yeah, because the rotor is the one that turning. Yeah, so you're turning the rotor and the rotor magnetic field cutting the stator and you have power out. So you need to know how to draw this, but this part here, when you're drawing the equivalent circuit, you should draw it, but most of the time we really care about this piece here. And just like a transformer, you have your armature react resistance, which is like your, will give you IA RA squared losses, and your synchronous reactance, right? So if you have this turning and it is stator windings, the VT here will be your output. Yeah, so if this is your output, if you use KVL on this little loop here, you'll basically have EA plus IARE. You really care about GXS when you're doing power calculations. And if you add EA and IA, get VT. But this is the main one. But now, if this is the output, this is where it will start. So if you want to change it up now, EA, and when you go through here, you will minus your losses across IA and RA, and that will actually give you what VT is. So you're just kind of changing up the equation based on the application. So the signs here will change depending on where the input is. So in our generator, it starts in here. And our motor starts in here. So it'll be VT minus the voltage drop across this will give you this. If it's a generator, EA minus the voltage drop across this, and you have a VT. So it's just based on where you started. So cool, right? So the motor, so we know the VT is starting here, so this is your input here. So you input your voltage supply, subtract your losses across RA, and you have your EA. Remember, there's a motor, right? So this part here is your armature. So this will be a rotating magnetic field, and then this part here will be rotated because I'm motor, right? Just note this switch up between field and armature from before, right? So when you're doing this, just know that this part here is the armature, this part here is the field. So that's kind of swap. Right. Okay, some equation, I mean, you went through this already, but things I want you to remember is that for EA, did I skip a song? I think I skipped some. I think I did. That I thought I didn't put this slide. But anyway, interesting. Yeah, so the angle for EA, this is called a load angle. And this here is the angle between EA and VT. Alright, and then, well, it's minus because it's a motor, because it'll be VT minus I. So voltage is always at reference at 0 degrees. This theta here is your power factor, just said before. And well, RA plus JXS is basically the impedance across the line, right? Most of the time, this does drop off, but we'll leave that to do the question. And same thing for the generator. Same concept now, but the sign swap. Because now the EA will be the output voltage plus the losses you got across IARE. That's based on perspective. Interesting. Right, next important equation is the armature current. So with the armature current, you're basically using the equation S as VI. But just note that, just like induction and synchronous, you must know the configuration which will give you V. S is just the load. Most of the time, the apparent power S, they'll give you that in the question. Because you're trying to draw a two-phase equivalent circuit, you have to divide the current by 3. Yeah, and most of the time, you have to divide it by root 3 in terms of the V. Yeah, so let's keep that in mind when you're doing the question. The I is different for induction. And just know the configuration. That will determine this bottom piece here. Right, so eventually these are the losses, these are normal losses, and the armature reactance. So, okay, so you can read that. But the armature reactance is basically a back EMF to rotation. So you can read that and know what the armature reactance is, right? And well, this is the circuit here. So basically, this part here is the armature reactance. So the total reactance on this side here is basically sum of that armature reactance and what the leftover one. But what the armature reactance is when you have a load, just like Lenz's law, you'll have a back EMF. And that back EMF is basically represented through this here. It will basically reduce the voltage drop across because that's the Lenz's law, right? So let's read the one from before, the armature reactance. And well, if you have any questions, let us ask. I don't want to spend too much time on this, right? Because theory. Know the equivalent circuit field, but that will help in the explanation. Okay, so load angle. So this will be first, but takeaways, the load angle is basically the internal EMF is equal to the mechanical position of the rotor with respect to the stator axis. This is important. Very important, right? Blah blah blah. So a negative load angle, we'll go through this just now. We'll go through the next slide. Cool. So I want to show you. So keep in mind that your stator is always your reference. Always reference. So in our motor, if you think about it, in our motor, you have the stator magnetic field rotating, and then the rotor trying to chase the stator. It will catch it, but when it catches it, it will still have a relative difference between that stator magnetic field and the rotor magnetic field. It's going to catch it, but it will lock, meaning the difference between them, it will just stay that difference. They'll lock onto each other. So technically, we remember this from I think I did that with you. So in this direction, whoever in front winning. So right now, the stator magnetic field leading. So he in front, and then the rotor, which is this one here, is lagging behind. But based on the angle, you have to measure it from the stator magnetic field, which is the reference. So this will be a negative angle. So yeah, for motor, you'll have a negative load angle because the rotor lagging the stator magnetic field because the rotor trying to chase the stator magnetic field. Remember, you're chasing a anti-clockwise direction. So whoever in front in the anti-clockwise race, basically leading, and whoever behind lagging. And for the generator now, remember the generator, you're turning the rotor magnetic field. So technically the rotor magnetic field will be in front because he's turning inside, and then that cutting the stator coil. So the stator will lag behind. So in this case, your rotor in front and your stator magnetic field will lag behind. But based on the angle, you always measure it from the stator. So this will be a positive load angle. Yeah. So you can think of it as who is pulling. In the motor, the stator pulling the rotor, so he will be in front. In the generator, the rotor pulling the stator, so the rotor will be leading, so the stator will be lagging. Always remember, it's measured from your stator magnetic field. So if you measure it from the opposite, you'll end up with a positive for this one and a negative for this one. So just keep that in mind. Why I need to know this? Because of the phasor diagrams. So the phasor diagrams, you have three possible ways you could ask it, right? You could ask it for a lagging power factor, unity power factor, or leading power factor, and yes, it will ask you to draw the phasor for it. Because the majority of the time, that is what let us build up to, drawing the phasor for the object itself, right? So when you're doing these questions, one thing I remember is that the J rotates a quantity of 90 degrees in the clockwise direction. What it means is when you're doing these equations, the RA part drops off. So instead of it being RA plus JXS, when you rotate it, it will just be JXS alone. So same concept, but that still be IA by just JXS alone. Yeah? When you're drawing the face, just keep that in. So easy way to remember this. So I'll have these steps in the next slide, but just remember this shows two things. The first thing it shows is the power factor, which is the angle between VT, which is always at an angle of 0, and I. The I will change depending on the type of load it is. So if it's a lagging power factor, it will be at the bottom. If it's a leading, it will be on top, and if it's at unity, it will basically be like a normal triangle, right? The angle is 0 degrees. Cool. And well, it shows the load angle. The load angle is the angle between EA and VT. This will always be on top. You will most of the time never find a EA at the bottom. So always going up in all of them, right? And then from these two, it just kind of like joining some lines together. But it doesn't really change much. Right? So I think the next slide went into it. So important stuff. So the power equations. With these questions, you must know these power equations because there's a lot of vectors when you're looking at the questions. You're basically resolving triangles together. So there's the first triangle that I resolve. So I basically resolve this triangle here. But one thing you have to keep in mind is that you have two triangles. You have the big triangle here and you have this smaller triangle on this side. But this portion here, they share in this piece. So for the big triangle and the smaller one, the vertical or comparatively the vertical component based on this here, both of them wouldn't be vertical, but based on what we see in here, they will share this side. But on the bottom now, this entire thing is one piece, and then this little piece here is the result for this piece. But really and truly, the power equation basically just come from resolving this triangle. So what I did here, basically resolve it for you all. So this is your theta. So if you're resolving your theta, you have your horizontal component and your vertical component. So your horizontal will be IAXS cos theta, and then the vertical will be IAXS sine theta, just like before, right? You will come to this just now, but just know this, how you resolve this tiny triangle here with IAXS. Right, the next one is the bigger one. So the bigger one, you have your EA, and you have your load angle. So that's like before, you have your vertical component, which is E sine load angle, and the horizontal component is E cos the load angle. Yeah. And cool. So when resolving it now, you're basically resolving the dotted black triangle into its vertical and horizontal components. So if you remember, this one here is basically this piece here. So this would technically be the vertical component. So IAXS cos phi is basically the same as E sine lower angle from the bigger triangle. And we're really doing it just basically remembering that P is equal to VT IA cos theta. You need to know these two and the basis of derivative here. And you end up with this one. So there's the first one. And well, Pmax will basically be when sine, we'll get to why Pmax is this, but Pmax will occur when your load angle is 90 degrees. So sine of 90 is 1, so you basically end up with this at the bottom. We'll get to this when you do the graph. The other part you're resolving is basically the horizontal component here. So for this piece here, yeah, remember is this here. So if I want this little piece, I want to subtract Vt from this entire thing at the bottom here. So that's what I did here. So it'll be IAXS sine theta, which is this piece here alone, well, that's equal to E cos lower angle, which is this whole thing here, subtract Vt. And I get this little piece here. For this one, you're using these equation for the reactive power. Yeah, and you just end up with this one. And well, same concept, just a different application, right? So Q will change, but that's okay. But the most popular one is this one here, for the real power. This one is more of that's a rare to see. Yeah, but most of the time I deal with the real power. But it's good to know the equation. Okay, never know what it could bring. Alright, so why this is your torque equation, your torque graph. So torque and load angle, obviously the max torque occurs when your load angle is at 90 degrees because sine of 90 is 1, right? So this is your torque equation. Oops. Can't call now. Can't call now. Anyway, yeah. So there's your torque. So same equation from torque T is P and omega S. So if this drop off, you get a max torque. But in the question, they could just ask you what is the torque. So if you just ask you what the torque is, you're just using this equation. You will have the load angle already because the system had to be operating at a particular load angle. Yeah, but if you want the maximum torque for that system, it would basically come from when sine of 90 is equal to 1, which is when the load angle is at 90 degrees. Now, well, voltage regulation, same concept. It will be EA minus VT and VT. So sometimes they ask you to calculate the voltage regulation for the questions. So that's not the equation. And this one, parallel generators, this is a theory question, right? You can read it through. What they're basically asking is why you will need to parallel multiple generators. Well, I mean, safety, to make sure do maintenance, you have more load, more generation. That's good truth, right? And also it have parameters that must be met in order to parallel transformers. So that's know that, right? Okay, cool. So the test, well, same thing as the test from before, but the first thing you do for a synchronous test is a rotor test. Same thing before, they'll give you the VDC and IDC, and you'll be able to solve for RDC. But with that RDC now, if it's a Y configuration, it will just be RDC and 2, and if it's a delta, it will be 3 and 2 RDC. Same concept as induction, but just note in the exam, will give you VDC and IDC. Remember, the rotor is basically a coil that's being fed by a voltage. So if you measure the voltage and the current, you can get the resistance. And based on the configuration, you'll be able to tell what the armature resistance is. Yeah, so let's know that. And well, the other one is the parameter estimation. So you have ZS and XS. So the first thing you'll find is ZS. They will give you V open circuit and I short circuit in the question. So this is a bit different from induction now, because you had to use your open circuit voltage and the short circuit current to get ZS. Yeah, and once you get ZS, you already know what RA is from before. So if you have ZS and you have RA, you'll be able to solve for XS using the powertrain or the load impedance triangle, right? Same concept, but just know the difference between ZS and XS and how you get it. You always have to solve for RA first using a DC test. You know, this one, I mean, they had to explicitly tell you that excess or area is negligible compared to excess for this ray. Let's know there's the first, or the second thing after the DC test, and there's the third thing to get excess. Okay? Cool. So steps to draw the phasor. So when you draw any phasor now, the first thing you do is you draw VT as the reference at angle 0. So you're just going to draw a line, VT, and this will be a reference. Everything going to be drawn from this reference line. After that, you get your load angle. You'll know what your load angle is from the angle for EA, because you will have calculated any questions somewhere. This is your load angle. This will basically tell you whether it's going up or down. Yeah. After you get that is what type of load. Basically power factor. Remember the power factor will give you lead, lag, unity. So that will tell you the reference for where I is. So if I at the bottom, you're lagging. If I on top, you're leading. If I in phase with VT, is a unity power factor system. So those two things are very important to know how the triangle is. After you do 2 and 3 now, you're just making some changes. So you're drawing I with respect to this angle from the reference. So when you have the angle, this down here will be I, and there's your power factor angle theta. Yeah, and then on top you will always have your EA. Just notice a phasor, so your lengths of your lines have to make sense based on the magnitudes of them, right? So if EA bigger than VT, just make sure the line a bit bigger than it. Yeah? So this giving you VT and I power factor. Now, the beauty of it now, VT, you're connecting it to the end of EA. So this piece here, you're just joining it to the end of EA. That is the first change, right? And the next change, now you're basically connecting the end of this I to that same point here. You're trying to make a straight line. Yeah, and that is it. Like it done. That's all it is. That is the whole thing. All you want to see is you represent your load angle properly. You have the magnitude for it. You have your VT. This will be at angle 0. You have I, you have the value for it, you have the power factor. And the last thing that you could put in is this. This line here is I excess. And you could put any value for that also at the end of it. And this triangle here will be for lag and power factor. Why? Because the angle between VT and I at the bottom. And that's the same steps they're going to be rinsing and repeating over and over. That's how to remember one thing. From the end of I going straight up to the end of EA is always a straight line. That's always a straight line. So when you're drawing the triangle, just make sure that the lengths are good enough that you can get a straight line between them. Yeah, so I'm gonna go back to so this is basically a lag, but here to here, straight line. There's always a straight line. Well, this one is basically unity, so it will be perpendicular. Same thing for this one. End of EA, straight up to the end of, I to E, so always a straight line. Always a straight line. Straight line, straight line. Just in this one, because EA is less than VT, the line itself will bend this way. Yeah. So let's keep that in mind when you do the questions. Cool. Well, really good stuff.